I'll begin. Heavenly Father, we thank you for this day. We thank you again for the break. I just pray that you would help us use the time wisely just to finish the semester well, that you'd help the students to refocus and just to use each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, I think I'm fresh out of stuff to lecture about. Do you guys got homework questions? It was,
No, go ahead.
It was close.
Yes. I have a question on 10.3, number 18.
10.3, number 18. I'll consider it. Let's see here. 10.3, number 18. Not this one.
Oh, never mind.
This one's got the equation of a tangent line.
Never mind. I'm just asking about, I had a question mark in my homework about it, so.
Oh, but I mean, it's fine. It's not about concavity.
Oh.
It's just tangent line. Here we got x equal to t to the fourth plus 2, y t cubed plus t, and we're supposed to find an equation of the tangent line at each given point. I'll pick the middle point. How about that? All right. So, first of all, let's see here, how to say this. The slope, I mean, we're going to use the things we talked about before the break, right? I guess the first order of business is what time does that point correspond to, right? Like the curve looks something like, who knows what it looks like, but this is a point on the curve, right? And we're trying to find the equation of this line. So the first question I have is what's t equal to here, right? What's the time? So how do you figure that out?
Can you just take 3 and plug it into x?
Yeah, 3 equals to t to the fourth plus 2. And we've also got minus 2 is equal to t cubed plus t. So this says t to the fourth equals to what? Yeah. 1. Which means that t is equal to what? Yeah, plus or minus 1. If you want me to explain to you why I know that, that's because this is t to the fourth minus 1, which is t squared plus 1 times t minus 1, which is t squared plus 1 times t squared minus 1. T squared minus 1 times t plus 1. And so if you put that equals to 0, it gives you just those two solutions. Those are the real solutions anyway. Time plus or minus I, whatever. Okay, so then the question, so great, time 1 or minus 1 are possible times. Which one of those work for this one? Because we have to have both of these at once, right? Minus 1? Yeah, I think, exactly. I think t equals minus 1 is what we need. Whoa. You turned a leaf. That was not exactly the wrong thing to say. This is good. I think, see, Friday Prince started giving wrong answers. I think maybe. I think you might have transferred it to him. So let's see here. So we're looking at time equals to minus 1. That's the time in question. We need to calculate what's dx dt. And well, what is dx dt? Dx dt is 4t cubed, right? And so x prime of 1 is what? Minus 1, rather. I can't, minus 1, right? It's like minus 4. Now dy dt is 3t squared plus 1, right? Which implies that y prime of minus 1 is what? 4, right? Yeah. So thus, the slope, m, if you like, is what? It's y prime of minus 1 over x prime of minus 1, right? Which is here 4 over minus 4. So we're looking for a line with slope minus 1. And what's our equation? So we know a slope and we know a point. By point slope, we get the following. Thus, y equals to, let's see here, minus 2 minus 1 times x minus 3. There's the equation to the tangent line right there. Now, what if we wanted the colliding parameterization of the tangent line? How would we do that? No. We say L of t equal to, what we do is we take the point, which in this case was 3 comma minus 2, and then we do plus t plus 1 times the direction vector. The direction vector here is minus 4, 4. It's direction vector. And the reason I put t plus 1 there is that when time equals minus 1, what happens? Yeah, we get that's 0, and this just gives us back 3 comma minus 2, right? So if you put time equal to minus 1, you get back the point. And so the parameterization, aka we have x equals to 3 plus, or 3 minus 4 times t plus 1, y is equal to minus 2 plus 4 times t plus 1. There you go. These are the so-called colliding parameterization of the tangent line. It's that parameterizes a line which, like here, this line, the same time, the time matches up in the sense that this point where they intercept is also time minus 1 for both the parameterization of the tangent line and the curve itself, if you wanted to do that. Now, the thing I boxed above is what the book is looking for here, right? It just says find the equation of the tangent line, so we can go back to y equals mx plus b, and that's a good description of it, right? But parametrically, this is also a description of the tangent line. So you're like, well, what's the answer then? Is it the equation or is it the parameterization? Depends on the question, right? You should know about both. All right, let me stop blathering on about this one. Do you guys have other questions? 10.378. 10.378. Well, a portion of a sphere of radius r is removed by cutting out a circular cone with a vertex at its center of the sphere. The cone, find the surface area removed from the sphere. Okay, so it's basically saying you've got this 2 theta, and you're removing this cap, right? You're cutting that off of the sphere. I guess the sphere has radius r. Oops, little r, he says. Now, I don't know if I actually did in here or not, but we have formulas for calculating surface area of surfaces of revolution. So the first thing to do would be to figure out how to describe, how would you describe this as a surface of revolution? I think basically we're taking this graph, right? Say just this piece right here, right? And we're rotating it around like that to form the cap of the sphere. Okay? So that's the surface of revolution. In the textbook, he explains how to calculate the surface area of such a thing in terms of the parameterization of it. All right? So that's the world in which we're living here. Now, if I can find where that is, that would be lovely. Where is it? Page 710. Yes. So let's see here. The question is, do we want to think about revolving around the x-axis or the y-axis? I say y-axis because it's just kind of more natural for me. Think of this as the y-axis. All right, so we're rotating around the y-axis, so to speak. And so the surface area is 2 pi, the integral, from a to b as appropriate, g of t, square root of dx dt squared plus dy dt squared, right? Dt. Now what's this? This is for x equals to what? F of t, right? And y equals to g of t. And we're assuming that the curve does not cross itself, which would be the case. We're thinking about, again, the curve we're actually talking about is, let me do it in a different color even. So I guess my question, this problem, number 78, you actually have to come up with the parameterization for the, you have to think, okay, well, this is a surface of revolution, right? So what should I make x and what should I make y here?
Is that red line like the top part?
That would be, in my view of it, that would just be this arc right here. As you swing that thing around, you get the cap. It's not the full circle, it's just an arc on the circle. May I suggest perhaps r cosine t? And r sine. Now, what would that'd probably be a bad choice, actually. I think a smarter choice here might be to actually view, you'll forgive me, I'm about to mess up my picture, but I'm not, here, you guys can deal, right? See, that would be what? No. That's not a 20. That's a 2. I see what you're saying. Theta, right. So if we want to make basically t equals to, if we want to think of theta as a variable, right? Yes?
Wouldn't that be the integral of ft and if you're revolving it around the y-axis, not the integral of gt?
Yes.
Did I copy the wrong one down? So I'm supposed to put I'm sorry. This is what comes with me not working things. Usually I draw pictures and derive these things. I just was foolishly following the book, and I paid the price of just copying the wrong formula down. Yes. Thank you. That makes, I think, more sense. Yes. That makes more sense. The basic idea here is that we're chopping it up into ribbons like this. And the the radius of the ribbon is x, and this right here, this ds, is the square root of x dot squared plus y dot squared dt. So you take this 2 pi, you get 2 pi x ds, that gives you the little bit of surface area, and then you add that up, that gives you the area of the whole thing. That's why there should be an f there, because it corresponds to the x, which corresponds to the ribbon, which is spun around the x. Anyway, I think it might be more natural. I wouldn't, maybe cosine is the wrong choice here. I think actually we do better to put sine t here and cosine t here. Because then if you put theta equal, if you put t equals to 0, what happens? This is a smarter parameterization because it makes our life easier. Because we go from t equals 0 to t equals to theta over there. So that would be my suggestion here. Yeah, Josh?
So, at sine and cosine with x and y is interchangeable then?
We can both parameterize a circle. So yeah. The question really is just what's your reference angle?
Okay, so this could not be applied to polar coordinates then?
If you did this to polar coordinates, they wouldn't be polar coordinates anymore. Polar coordinates says that the angle is swept out from the positive x-axis in the counterclockwise sense. So here t, as I've defined it, is not the polar angle, but something else. And it's also sweeping clockwise. See that? But that's natural for this problem because then my integration region just goes from 0 to theta. Theta is an arbitrary thing which is given in the problem. I want the answer to be in terms of it anyway. This makes less work for me in the totality of it. That just works out to r. So you end up with the integral of like r sine t times r dt with 2 pi. It's not bad. Well, I did want to talk about surface area at some point. Now I have. Woohoo! So there you go. We treat surface area in much greater depth than Calculus 3. It's just kind of a passing, hey, look, we can calculate surface area here. It's not really the end of the discussion, okay? Just the start of one. Yes?
I have a question about 10.3, number 54.
10.3, number 54. Oh. Find the arc length of the involute. You sure this one? 54?
Yeah, 54.
All right.
Yeah,
We have x equals to cosine theta plus theta sine theta. We have y is equal to sine theta minus theta cosine theta. These describe, as he says, the involute of a circle. All right. And we're supposed to find the length of the arc for 0 to 2 pi. All right, so. Supposed to find the arc length of this curve. So the involute is something you can form from a given curve. I think it has to do with following its tangents or some such thing. It's interesting, but telling you about that won't help you solve the problems. Let me focus here. So to find the arc length, what do? I mean, S equals to, yeah, very good. Yeah, fair enough. Find the derivative first is good advice. So x dot equal to, Yeah, minus sine theta. I'll use primes here. Why not? Y prime cosine theta minus cosine theta plus theta sine theta. So that's kind of neat. So we get theta cosine theta and theta sine theta for the x and y derivatives respectively. And consequently, the arc length s would be the integral from 0 to 2 pi, the square root of x prime squared plus y prime squared d theta, right? Calculate the arc length. Yes, Josh?
How does the derivative of x and y equal 3 terms?
Product rule. Theta and sine theta, these are both functions of theta. We're looking at a product of functions, so we have to do the product rule. So
Why aren't we using 2 pi, this arc length?
that's not arc length. This is, I was trying to make that a big S. I forgot to give it its decoration, or sometimes even better yet, S dot A dot. Surface area. This is the surface area. This and
This is arc length.
this is arc length, yes.
Oh, okay. All right.
So we integrate the square root of the sum of the squares of the velocities. That gives us arc length. Now that is what? I mean,
That's what I messed up there.
this one actually looks kind of fun, right? Well, anyway, if I write much more, I'll do the problem some bitch stop, but this one's not, I mean, once you see that, it's not bad, right? Did you guys see how to finish? Factor out the theta squared, right? And what can we say about the square root of theta squared? Generally, it's the absolute value of theta, right? But the absolute value of theta is equal to theta for theta non-negative. In particular, if theta is between 0 and 2 pi, we can drop the absolute value and just write theta there. That should be in your thinking. Whenever you take the square root of something squared, you've got to ask yourself the question, am I supposed to put in a minus for certain cases? Right? If you're not aware of that, it can get you. I like to get students in differential equations on this. It gives me joy. Sorry. Not really. I try to warn them, but they don't take the warning. Other questions? Yes, sir.
Maybe we don't have time for this now.
I probably do.
We'll take a look. 10.4, number 104.
10.4, number 104. I see. So you're trying to... Oh.
We can certainly postpone it for right now.
Well, we can start the discussion. Why not? No one else seemed to have a pressing question, so... There are definitely things I haven't lectured in here yet on, guys. So as you're running through the homework, you know, you hit something you don't think I've said anything about. It may be the case I haven't said anything about it, and I'm waiting for you to ask me about it. Okay? So do keep that in mind. I'm not sure this is one of those things, but I'll take a bite. 104 of section 10.4. We're supposed to prove that the tangent of the angle well, it's not that, psi, 0 less than or equal to psi less than or equal to pi over 2 between the radial, so this is psi, it's between radial line and the tangent line. Radial line and tangent line at r theta on graph r equals to the polar graph, f of theta, is given by tangent psi equal to absolute value of r divided by dr d theta. Okay, so here's a picture. So here's our function. All right, this is r equals to f of theta, all right? And he's picking a point, like let's say here, right? And so there's two things you can look at there. There's the tangent line, right? Now, certainly, if we're given specific formulas for f, we can characterize that a number of different ways, right? We could find the parameterization for it. We could find the equation of it as a Cartesian line if we wanted. These are options that are available. But it's the angle between the tangent line and what? And the radial line. The radial line is what it sounds like. It's the line from the origin out like that. This is the radial line. Of course, this is in his picture, right? And so the way I drew I picked a different kind of, here, so he sweeps psi from the radial line to the tangent line. So I think, oh, I guess I have to go. I guess it's this way, huh? In my picture, it's that. And he's picked a point down here, so let me try a different one. Like down here, we'd have this tangent line, right? We'd have this radial line. And down there, well, I guess it's the same. It looked different to me. So how do we capture that angle as it relates to the radial line and the tangent line to the curve? You had an idea, Josh? No? Well, the thing that I think of right offhand would be to measure the angles. Of course, if this point here is r theta, right? Then you can see that what angle the radial line is at theta, right? the angle of the radial line, so to speak. Right? By definition, that's theta. Right? So let's forget about this thing down here. Get out of my way. All right. That's theta. And let's see then, what is, how does psi relate to theta? I mean, I've drawn these so they look perpendicular, but that's not, doesn't have to be the case. I mean, the polar curve can be, you notice like over here, this is the tangent line, right? And the radial line is like this, right? Those are not perpendicular. It's just a coincidence of my picture that it appears that the radial line and the tangent line are perpendicular. It's actually more complicated what exactly is happening. How is that?
It's difficult because we don't have to pair parallel lines that we can apply on those equal reference to.
So in the title to this course, what does it say? Right. So this is that second part of the title. I mean, I can do things that are perhaps helpful here. The slope of the tangent line, right? What is it? Or maybe better yet is the direction vector. I think that's more, to me that's more useful. So it would be, what we do is we do dx d theta, dy d theta, right? That gives me a vector which points in the direction in which the graph is going. Now, specifically that, what is x here? X is equal to, well, it's equal to r cosine theta, but in this case, that r is actually f of theta cosine theta. And y is equal to, by the same token, f of theta sine theta, right? So the direction vector of the tangent line, what is it? It is, you got to do the product rule, just like we did in that example there. So we got df d theta cosine theta minus f of theta sine theta, df d theta sine theta plus f of theta cosine theta. So just to try to explain what was the significance of those things I just wrote down. If we look at the curve, right? Right? And maybe I should make it bigger. So I pick this, pick this point wherever, right? Then if I was to draw a tangent like this, right, in the direction in theta, which is if theta goes this way, right? As theta is increasing, we're sweeping that way, I believe. I could be wrong about this, but let me just assume f is not weird. if this little leg here, this little triangle, right? That's a little direction vector I'm thinking of, okay? Well, if I call this thing, for the sake of not writing all that again, A, and if I call this B, well then this is A and this is B here. The dy d theta, the dx d theta. That's the tangent line, right? But then the question that I'm struggling with, of course, is how to connect that to the radial line, right? Now the radial line is here at theta, angle theta by construction, and what's that? This angle here. This angle here is what? Is I think by definition psi, right? Right, we sweep from the radial line to the tangent line. That's how he's defining this psi. Ooh, this picture works for me. See, because what I can do here now, I see it. I start to see it. I just go like this, right? Now there's those parallel lines you're looking for, Nathaniel. See, this line parallel to this one. So by high school geometry, we know that theta is also found right here. I mean, these are alternate interior angles or whatever. Or is they alternate? Or I don't know what they are. They're the SAS or the, what's that? Corresponding. Okay. Once upon a time, I tutored high school geometry. I learned those terms for about a couple months, and then I forgot them. Look here, but there's something else you can do. There's another piece in the puzzle here. This is what we might call beta, just to give it a name. And you see what we have. We have that beta plus psi plus theta equals to what? Yeah, pi. Now, I'm not sure that actually helps directly. But what else can you say about beta?
Isn't beta actually x?
That doesn't have to be 90. Yeah.
Yes. Okay, so beta doesn't have to be.
See, but beta involves the tangent of what? Beta is tangent of. Now here I might get into some trouble in terms of the signs. See, because in my picture, at least, in this particular situation, it's the case that A is negative, right? So if I want the acute angle here, I actually need to put like a minus A here. You know? Yes? So I'm thinking the tangent of B. Oh, I'm sorry, tangent of psi rather is equal to B over minus A, I believe. Oh, I'm sorry, tangent beta. I'm sorry, guys. But tangent psi is what? Tangent psi is equal to the tangent of pi minus theta minus beta, right? Tangent is pi periodic. So that's the same as the tangent of minus theta minus beta. Tangent repeats itself. you shift by pi. Then you need the adding angles formula for tangent. But when you do that, it brings in these to play, and something nice happens. And it just drops back down to, I guess the other question is, what is dr d theta? What's that mean? Oh, dr d theta is what here? Keep in mind that in this context is what? It's df d theta, right? And you see there's df d thetas appearing in here. And there's an indeterminate number of algebraic steps in between what I have on the board and what's claimed. But yeah, when I look at a problem like this, I don't know what to do until I just start. What do I do? Like, what's my method, guys?
Draw a picture.
Right, I draw a picture. I try to gather information that I know. Sometimes just writing, even though I don't know what to do with it yet, the process of writing down what the tangent line's direction vector looks like, it's helpful for me. Now, this direction vector idea wasn't necessary. You could have gone straight to the slope of the tangent line, right? Eventually we get back to that anyway. This is this tangent beta, that's the slope of the tangent line, which is something like rise over run. See, that's not quite honest because it's the wrong. Anyway, I shut up. I think I'm only going to hurt my case if I go on. So tomorrow, more homework questions, yeah?